Thanks, Andrew. Thanks, everyone, for joining me. So, yeah, as Andrew said, I've got sort of 2 hours worth of material to get through with a nice break in the middle where we can have some sweets and a bit of a chat. So let me give a bit of context. So maybe a good starting point for the audience is to look at the audience in front of me and say, how do people here like to study the long-time behavior of Markov chains? Because I'm sort of going to focus on one particular approach, but you know, already from people who I've seen give talks since I've been here, there's people using conductance methods, people using Lyapunov methods, and people using sort of everything in between, nice couplings and so on. So that there's all sorts of ways of going about the long-time behavior of Markov processes. There are some sort of unifying principles that people might stick to when trying to do a given analysis. And so some particular principles, which I think, you know, are very sweeping in character that people might look at, you know, one class would be to take probabilistic approaches somehow. So Alex Watson was here earlier this term, and I asked him, you know, what do you think distinguishes a probabilistic approach to a problem? And he would say it's when you're looking at pathwise behavior of a process, then it's usually quite probabilistic. Okay, so this often means things like looking at couplings of processes, regeneration times, and in some sense, local behavior, although that's a bit vague. And another strategy for looking at the behavior of Markov processes is instead to go sort of functional analytic in character. So instead of thinking about what an individual process does, you sort of lift your thinking to the level of the Markov semigroup, how it's spreading mass around the space, and thinking about convergence in terms of sort of, let's say, information theoretic things like divergences and entropies and so on. And there's somehow a global character to this, which I'll be a bit vaguer about. So to give context, right, I have a lot of appreciation for the former approach. I like a coupling as much as the next man, and I've sort of given talks about that in the past. When it applies well, it's very powerful. For me, in the past couple of years, there have been some specific applications where it wasn't really suitable, right? And that got me very interested in this latter functional analytic approach, which has sort of been reasonably productive. And so the goal for today is to sort of share some of why I'm enthusiastic about it and point to things that I like about it that you may be able to see in your own work and, you know, adopt them from there. Yeah. Okay, so some motivating questions. So things that might be on your mind that I hope to give a bit of clarity on before the end of the talk. So one is actually, what is a functional inequality? This may be a new term for you, so I sort of want to clarify what that is. And also, what are the standard functional inequalities? It's a sort of very big field, but there's maybe 2 or 3 that people are talking about quite a lot of the time. I'd like to give intuition for when you should expect them to hold, right? So to have an intuition for what kind of probability measures or Markov chains will give rise to these things. And if these inequalities do hold, then what are their consequences? So it's sort of a bidirectional intuition, if you like. From a practical point of view, so I want to give some intuition for what settings you can expect this to be a good approach for, right? You don't want to hit every problem with the same hammer, and so I want to give some insight on why a functional analytic approach was relevant for me and why it might be relevant for you. In my case, I found it was quite easy to use, and there were certain details of the process that this approach can be quite robust to, which was nice for me. Another thing that I'm hoping to emphasize along the way is that, you know, these are sort of complementary methods to be sort of more probabilistic and more functional analytic, and these things do feed into one another, right? So often if you've used, you know, say a coupling method to obtain probabilistic insights on the problem, you can often deduce functional analytic properties of the semigroup from that, okay? So you're not throwing away everything you've learned before, they're sort of fitting together nicely. Okay, so the course grain plan, so I'll give a bit of a prelude on why take a functional approach in the abstract. Why might that be a nice way of looking at convergence? Then the rest of the first hour, or 50 minutes, or whatever it turns out to be, will explain how functional inequalities look in the case of reversible diffusion processes, and, you know, really quite narrowly most of the time for the overdamped Langevin diffusion, where things are very well understood. And I can give quite a complete story there. Then we'll take a little bit of a break, and for the second half, I will talk more about discrete time Markov chains, which are what I've been working on a lot for the past 3 or 4 years, and explain how to use these techniques for practical MCMC algorithms, let's say. Okay, so there's necessarily compromises. It is a short course, right? So because I'm time limited, what I'm going to try to do is give broad strokes of intuition and be generous with references and skip over details along the way, right? And I'm here in Cambridge for another few weeks, so there's plenty of conversations we can have after the fact. You know, this is not so controversial, but I'm really focusing on the Markov chain side of functional inequalities. So, you know, these inequalities have lots of implications for things like geometry, concentration of measure, even information theory and stuff like this. And I mostly won't get into that, but there will be references. I will mostly focus on Markov chains that are reversible, and I will mostly look at convergence in an L2 sense, but not exclusively, again, because the story is cleaner here and I can give the intuition there. But I would emphasize that more is possible than what I'll say there. And finally, because of the type of thing I work on myself, the examples will largely be drawn from contemporary MCMC rather than from more general stochastic processes. Okay, so these are, apologies if you like, but I think it's a nice way to set things up. Right, so I basically learned most of these techniques in the past 3 or 4 years on the basis of collaborations with these three. So this started with the sort of first project of my postdoc, and we've since done a number of other works together using functional methods to study practical MCMC algorithms. Okay, yeah, good proviso. It's a tutorial. Stop me at any point if you're not understanding what I'm saying. There's plenty of stuff that is manifestly skippable. So let's make use of that. Another warning, which is very specific to this thing in particular. So partially by having spoken to certain people the past couple of weeks, I'm using the word robust a lot more than I used to. Now, this is not a very useful word in isolation, so anytime I sort of describe something as being a robust approach or a robust strategy, if by the end of the slide I haven't clarified what it's robust to, then you raise your hand and you tell me off and I will sort of clarify things. Okay, and hopefully I will pass this test, but we will see. Okay, before I say anything interesting, this is sort of standing notation for most of the talk. So pi is the probability measure I'm interested in sampling from. P is the Markov semigroup or Markov kernel that generates the dynamics that we care about. Typically, it will be reversible and positive. Sometimes it won't matter. Okay, mu naught is going to generically denote where I start the Markov chain from, the distribution I initialize at, and the law of the Markov chain at time t will be written as mu t. And the overall strategy is to quantify the way in which this measure mu t converges to pi as the time horizon goes off to infinity. Okay, nothing interesting here, but this is what I mean. Okay.
Do you mean positive in the sense of mapping positive functions to positive?
So I mean in the spectral sense.
Positive definites.
Yes. Yeah. Thanks. Okay. So why take a functional approach? What are different ways of measuring convergence, and why might one be preferable to the other? So this here is Alfred Rényi, who's an information theorist from the 1950s, who cared very much about this question and gave sort of several answers to it. Okay. So let's talk a little bit about some notions of long-time convergence for Markov processes. So one that I think people often intuitively have a good feel for is total variation convergence, right? To sort of say, if I have two probability distributions and I can generate coupled realizations of them so that they're with high probability very close to one another or sort of exactly overlapping, that's nice. And so if our Markov chain is converging to the distribution we care about in total variation, it is in some sense indistinguishable from a real sample. And for many applications, that's exactly what we want. Okay. Now, what's a bit challenging about total variation is that it's a bounded distance, which means that it's often quite difficult to contract it, okay, to show that it's sort of shrinking uniformly in time. And so that usually leads us to looking at other ways of measuring convergence first. So we show that something bigger is shrinking very quickly, and hence total variation also will be. Okay, and so something people might consider in lieu of that is what I would call a weighted total variation distance, where I put some weight function, lowercase phi here, which sort of weights different parts of the state space. And this is quite closely related to Lyapunov function methods implicitly. That's a very nice connection sort of elucidated by Hairer and Mattingly about 16 years ago. Okay, so that's a different way of measuring convergence, but it requires you to choose this function phi that tells you what parts of the state space you care about somehow. So this is something that you can show to contract in various settings, but it's not necessarily quantitatively fantastic in various cases. Now, another thing you could look at, which is sort of increasingly popular the last 10, 15 years, let's say, would be to measure convergence in some sort of transport distance, right? So what I've written down here is sort of the transport formulation of the one Wasserstein distance, as it's normally known, or the Kantorovich distance, where you say, two probability measures, they're close if I can generate samples from them in a coupled way, such that they are spatially close to one another. So they might not hit each other exactly, but at least they'll be sort of physically close to one another. So that's very much tied to sort of coupling and contraction methods in the X space, if you like. And for very nice processes, this is a fantastic way to analyze them, really. For sort of your nice, sort of strongly convex and monotone setting, things behave very well. But as you move away from that, things become quite a bit more challenging. And so there's a challenge arises there. And then there's another category of measuring convergence, which sort of overlaps with total variation a bit, which is what I would call information theoretic convergence. Okay, and so this is a notion of convergence where you don't care about where in the state space you are, as long as it's difficult to distinguish it from a true sample in some sort of classification-based sense. Okay, so I'll talk a bit now about information theoretic divergences. So internally I call these density ratio divergences because they're defined in terms of the density ratio between the two things that you care about. They're also widely known as F divergences or phi entropies. I think this is a useless name because it just tells you that there's an F or a phi involved in the function, which is not particularly useful. Nevertheless, if you see it in the literature, that's what people are referring to. Okay, and so what do? We take capital phi to be a convex and non-negative function, which is equal to 0 when the input is 1. And we define a divergence between P and Q by saying, look at the density ratio between the two measures, apply the convex function to it, integrate that with respect to Q. Okay, so by Jensen's inequality, amongst other things, you can see that this is going to be non-negative. It often qualitatively behaves like a distance or like a squared distance, but we won't really need to use that. Okay, and so there are many examples of divergences of this form that we use routinely. Total variation is a particularly nice one, where the phi is sort of, the modulus of r minus 1. Okay, there's also sort of relative entropy or Kullback-Leibler divergence, the chi-squared divergence or Pearson divergence in some circles, and also the Hellinger distance also fall under this umbrella. And so many things are very well understood about this class of divergences. The useful thing in some way is that most of the time, if you have convergence with one of these things, if this guy is going to 0, then it is also going to 0 in total variation distance. Okay, and people tend to be happy on the grounds of that. Sometimes you care intrinsically about converging in these other divergences, but often it's just instrumental. Okay. So information theoretic contraction. So if I want to show convergence, the nicest kind of convergence tends to be exponential contraction uniformly in time. Right, so if everything goes well, I'd like to be able to show that the divergence between my law at time t and my invariant measure is shrinking at some exponential rate c, and not eventually, but actually always, with constant 1 in the front. That's sort of the nicest thing we can go for most of the time. Now, I could assume that this is the case and we would be done, but I'd say that's not particularly useful, right? We would like to get something a bit more checkable or concrete or intuitive that guarantees that this holds, right? And so this is an exponential decay result. And what's our favorite way of proving exponential decay results in maths? I would say it's usually Gronwall's inequality, right? You show that the rate at which something is changing is proportional to how much is left. Okay, and so we can try reverse engineer this or sort of use the reverse Gronwall method, right? So that's the two of them. Gronwall and reverse Gronwall. Okay, so what is that going to be? So we're going to say, so look at this divergence that we care about. We know that it's going to be decreasing in time by sort of data processing inequalities and stuff like this. So it's natural to differentiate it with respect to time and put a minus sign in front. So that's sort of how much things are dissipating by. And take its value at t equals 0. Okay, and I'm going to call that the sort of phi information of mu naught with respect to pi, let's say. And so if we want to enact this Gronwall idea, we want to show that this information functional is lower bounded by this entropy functional. And if that's true, then we're sorted, right? So this is something nice to aspire to. I would say a priori, describing this strategy, it seems a bit optimistic. We're sort of supposing what we want to eventually be true and then trying to reverse engineer it. Sometimes that's a good strategy and sometimes it's not. I will say in this case, history has shown that this particular instance, it's a very fruitful strategy. And looking at these inequalities here can get us quite a lot. Okay, but this is still quite abstract, so let's take it to a more concrete setting where these divergences and informations look, familiar, let's say. Okay, so here the tutorial properly begins. So we're going to look at reversible diffusions or the overdamped Langevin diffusion. So I'm sure many of you will recognize this gentleman on the right, who is one of the first people to look seriously at Brownian motion as a stochastic process, let's say. On the left is the physicist Paul Langevin, who sort of introduced the underdamped Langevin dynamics, as we would call it now, but is sort of indirectly responsible for what I will call the overdamped process as well. Okay, so let's give a bit of an overview of this. Kind of a whistle-stop tour, but I think this will be familiar to many people here. So let pi be a probability density on a Euclidean space. I'm going to write OLD of pi for the Ito diffusion, which has this drift and this diffusion. So essentially, you should think of it as having some drift pushing you towards the modes of pi and some diffusion that's sort of isotropically exploring the state space. So I think I might mention this again, but This is a pi reversible ergodic diffusion under very mild conditions. As you send the time horizon to infinity, you do indeed converge to pi. Now, to do maths with this, it's going to be useful for us to define this semigroup P of t, which says, so PTF of x, it's saying, if I start the process at x and I run it until time t, what is the average value of the f after I've run it for that amount of time? Okay, so this sort of has a smoothing effect where you're averaging out over the locations where the process could end up. So that's a very interesting object for us. If we can sort of understand how this semigroup is acting as time goes to infinity, we have a lot of information about the process. In general, this semigroup itself is not particularly tractable, right? In a sort of Gaussian case, you can write down what the semigroup is going to do, but more generally, it's sort of, something we can describe, but not write down nice formulas for. So what do? We again sort of differentiate at 0, right? So we can define the infinitesimal generator of the process by essentially saying, okay, when t is close to 0, the semigroup will be close to the identity, right? If the process doesn't move very much, then the function value shouldn't change very much either. So we can construct the generator according to this definition here, and then we sort of formally recover that the semigroup is the exponential of this generator in time. Okay, this is all sort of quite standard stuff. Following this thing on the right-hand side, you can see that if you differentiate the semigroup with respect to time, you can, the generator shows up downstairs, either on the left or the right. It doesn't matter because they commute with one another. And so we'll use that momentarily. And so concretely, this generator has a very nice interpretation, right? You have this say, okay, how will a function change over a small period of time? Well, we will sort of drift a small amount in the direction of grad log pi, which is what this first term is reflecting. And also we will diffuse in space, which is what this Laplacian term is reflecting. Okay, and so the fact is that this generator, even though it's infinitesimal, it gives us a lot to do actual calculations with, which is useful for us. Okay, I think I'll introduce a few more concepts. So another useful object is what I would call the Dirichlet energy form, right? So it's defined for sort of nice enough functions f and g. And so what do? You take f, you apply the generator to g, you multiply those two together with a negative sign, and you integrate this against the invariant measure. So if I don't specify, the expectations will always be with respect to this pi I've talked about. Okay, so if you do a sort of simple integration by parts trick, you will see that it's actually the same as looking at the gradient of f and the gradient of g, taking the error inner product and integrating that. You see from this that it's sort of a symmetric bilinear form as well. And sort of some other considerations can let you see that it's positive semi-definite. Okay, and so this will be used sort of a small handful of times in this section. And it provides quite a useful language for describing how these entropy functionals that I was talking about, how they will decay over time, how they will dissipate, right? And it's a particularly useful tool for reversible processes more generally. Okay. So let's go back to talking about functional stuff. So as I said, we'd like to make statements that say, this density ratio divergence is exponentially contracting as a function of its initial value. Now, that's a sort of statement about measures, right? But a nice trick is that actually we can turn it into a statement about functions, which will turn out to be more tractable in various ways. Okay, so using the reversibility of the process, it's not horribly difficult to show that the density of mu t, so the law of where you are at time t, with respect to the invariant measure, it can be obtained by looking at the initial density and propagating it through the semigroup. Okay, so that's a nice sort of half-page exercise if you like. And so instead of thinking about these divergences as acting on probability measures, we can think directly in terms of the functional densities, right? And so if I define the phi entropy of now a non-negative function f to be the expectation of phi of f minus phi times the expectation of f, and by Jensen's inequality this will be non-negative, right? Then the phi divergence is directly expressible as the entropy of the initial density propagated through the semigroup, okay? And so what this shows us is that actually, if I can show that the entropy of any function passed through the semigroup is decaying nicely, I can get these nice measure theoretic consequences back from it, okay? But working with functions will allow for sort of more explicit computations in various ways, okay? So this is sort of the functional trick. You go from looking at measures to looking at functions, and you can differentiate them as you like. Okay, so now let's do some computations and see how this actually looks in practice. So for a generic, non-negative f, let's say, if I do the negative derivative of the entropy with respect to time, this is what I'm differentiating. The other term is a constant, and so it drops out. Right? Now, by the chain rule, I differentiate this first term, and I pull out the derivative of PTF, which, as I said before, you can get by applying the generator. Now, what is this? This is a function. This is minus the generator applied to a function. So that's a Dirichlet form, okay? And I can write it as such. And then using the fact that the Dirichlet form for the Langevin diffusion has this inner product of grad f, grad g form, I can simplify the expression, okay? And so now the dissipation of this entropy has this very explicit form here, involving the sort of gradient of the observable, if you like, and then this extra rate phi double prime. Okay, and so this is, as I was saying, a sort of information functional, which is just sort of classically what a derivative of an entropy looks like. Okay, so that's something we might be able to do something with. And so I'm going to say that the probability measure pi, and implicitly, the Langevin diffusion on that measure, satisfies a phi Sobolev inequality with constant c if for all suitable functions f, you have this dissipation estimate, right? So I'm really taking what I have here and replacing PTF throughout just by some generic f, right? And so this term on the left is somehow an energy functional, right? And what we have on the right is the entropy function. So if this is true, then we can sort of crank the Gronwall machinery and get the estimates that we want out of it. And so this is what we're going to pursue for the next half an hour or so, let's say. So just a quick note, so my convention here is that the constant c is the rate of convergence. I want Markov chains to converge quickly. I want c to be big. If you look in the literature, sometimes the Poincare constant is the inverse of this guy, and they want it to be small. Okay, so that's just something to keep an eye out for. Okay, so any questions thus far?
What function should be to get a log of the?
So I will say that very soon, but it will be sort of r log r, something like this. Yes, okay, so I can mention here, so if this perspective is appealing to you and you want to learn more about it, this paper of Jalil Shafai is very readable. He sort of studies very general convex phi, for which a lot of conclusions hold at that level. But if you want the really powerful results, he studies sort of r to the p for p between 1 and 2, and also the limiting case as p goes to 1, which is this r log r, right? And for those results, it appears crucial that you have convexity not only of phi, but of its second derivative and the negative inverse of its second derivative. And I think getting real insights on that is a bit challenging, but you can get particularly strong results in those cases. Okay, and that's what he looks like. Okay, so to come to the question, so these phi Sobolev inequalities are quite general, but in a way there's two that really matter from my point of view, that are sort of very widely used. So one is when you take the sort of function phi to be quadratic, this leads to what is known as the Poincare inequality after Henri Poincare. And when shuffling the terms around a little bit, you can also write it this way. Somehow for general functions f, that you can upper bound the variance of the function by this sort of energy term, okay? So it's sort of the interpretation I like to give is that the right-hand side is saying, is the function flat locally in some sense, right? And the left-hand side is the function flat globally? Does it have a small variance, okay? So that's a nice interpretation of that. The other one is when we take phi to be this sort of quasi-logarithmic term, and we get what's called the logarithmic Sobolev inequality. So that's sort of not directly introduced by Sobolev himself, but it's a sort of derivative of these classical Sobolev inequalities, which are used in PDE predominantly. And so I'm about to do a very lame joke that I got from a friend. Of course, who I should really be citing, it's log Sobolev. Okay, but no, this is him sort of at a more advanced stage in his career. Okay, so yeah, so right. So the log Sobolev inequality, if we translate it from the previous slide, it looks like this. So you bound the sort of logarithmic entropy of f by this functional over here, right? In some cases, people like to replace f by f squared, and you get this different formulation, right, where you have the entropy of f squared on the left and the classical Dirichlet form on the right-hand side. People like that because it makes it too homogeneous as an inequality, so it's sort of directly comparable to the Poincare inequality at that stage. A sort of brief comment to make about that is the equivalence of these two things relies on the fact that on Euclidean spaces we have a chain rule, right? If I start working on discrete spaces, the equivalence of these two inequalities is actually not so clear. We'll touch on that in the second half. Okay.
You say that Poincare inequality holds for what function?
So I think the usual statement is sort of L2 and locally Lipschitz. Yeah. So
I say global constraint and local.
Yeah. But it's any time that both sides of the equality make sense, you'll be okay.
In that case, you would say that pi satisfies.
Yeah.
With some gamma, the best gamma.
Yes, exactly. And so as I said, we want gamma to be big, typically.
You want it to be big for all functions.
Yes. That it holds uniformly in these F is very important. It essentially says, no matter what the initial distribution is, you will still converge like this. Okay, so let's talk about why these are the important ones, right? Okay, quickly, so they are not equivalent to one another, and one is strictly stronger. Okay, the log Sobolev inequality always directly implies a Poincare inequality holds with the same quantitative rate. Okay, and in principle it could be better, but at least you guarantee that it's at least as good. And the rough idea is that if you look at the phi for the log Sobolev inequality and you expand it around r equals 1, it looks like what you have for the Poincare inequality case. And so there's a sort of very simple argument that allows you to go from one to the other. So not only does it imply the Poincare inequality, but it is strictly stronger. I will give you examples shortly of things that satisfy some log Sobolev inequality, but no Poincare inequality. Sorry, vice versa. Okay, and so why are these the relevant cases in practice? Well, in a way, they are sort of the edge cases of where this technique can work, right? Because if you have an inequality that is weaker than the Poincare inequality, it tends to be associated with slower than exponential convergence to equilibrium, okay? So if I had a sort of more permissive inequality than a Poincare, it would not behave quite as nicely in that way. Similarly, you could make an inequality which is stronger than the log Sobolev, but it will not be able to tensorize in a way. So if you have something which has sort of better convergence to equilibrium than the log Sobolev inequality would imply, and you take products of that same process, at some stage the central limit theorem kicks in and it slows you back down again. So I'll sort of touch upon this later. But so there's the sort of boundaries of the robust good case in terms of being robustness to putting it into high dimension. Yes?
Can I see the extremality of these two function inequalities? The gradient functions and the quasi-logarithmic function inside the family of phi.
So sorry, what's the question?
Inside your choice of phi entropy, you have the phi functional.
Mm-hmm.
Can you see the extremality of these two functions inside the family of phi?
So I'm not sure, because you can have functions that grow faster than quadratically that are still valid there. So I think at that level it's harder to see, but at the level of the process is how I tend to understand it. Yeah, but it's an interesting question. Okay, so let's give some illustrative examples of when these things hold. Okay, so the sort of flagship case for the log Sobolev inequality is to look at probability measures with a density which is strongly log concave with some constant rho that's greater than 0. You should really be thinking of a standard Gaussian in this case with variance 1 over rho. So the idea is you sort of translate the density into the potential function, you look at its Hessian, and you say it is uniformly bounded away from 0 in this way. So under this condition, you get that the logarithmic Sobolev inequality holds with this constant rho. So it's a non-perturbative result. It's really as long as you are at least this convex, things are at least this good, and you have this form. Of course, as I said, you will get the Poincare inequality for free out of this. Okay, there's many ways to establish this. I'll comment on a few of them shortly. Actually, this is sort of the nicest possible case for any diffusion process, I would say. So once you have this, you can employ something called the gamma calculus, developed by Dominique Bacry and Michel Emery, and you can get all sorts of results even stronger than, even richer than the log Sobolev inequality, let's say. Okay, and so if you're interested in this sort of stuff, this is really the book to look at, where they sort of, from my point of view, they take this assumption and they look at everything that it might possibly imply and all of the various interesting consequences that it has. Of course, it has the risk of being somewhat brittle, right? This assumption of uniform strong log concavity is quite a rigid one and certainly does not cover all cases of practical interest, okay? But it's a very good starting point for understanding why these inequalities fit together as they do. Okay, so another example to sort of hit at this sort of boundary effect. So focus on the exponential distribution on the positive reals. So, the waiting times in a Poisson process, or however you like to think about it. Okay, so for this, you get that the Poincare inequality holds with constant 1/4, i.e. that the variance is upper bounded by 4 times this gradient norm. How do you prove this? Essentially, it's a one-dimensional problem, right? So you can study the sort of eigenproblem associated to the Poincare inequality quite directly and actually find what function saturates the inequality. Okay, so it's sort of explicit computations in a way. You can show without much pain that you can't get a constant better than 1/4 by trying exponential test functions and seeing when they stop being integrable, basically. And to show that it's sharp is, again, a little bit more work, but quite explicit computations. In this case, the logarithmic Sobolev inequality cannot hold with any finite constant, right? And I'll comment on why this is the case shortly. So these are our sort of toy problems to get started with. And you can take my word for it at this stage. Okay, and so that's not so interesting by itself, right? Because these are sort of very well studied things in isolation. We'd like to be able to look at more interesting probability measures pi. And so what are we going to do? We're going to describe some sort of algebra for putting functional inequalities together and transferring them between different processes. Okay, and so here's a sort of bunch of them that I will talk you through. Sort of tensorization, transport of measure, convolution, change of measure, and taking mixtures. And there's a few others I'll comment on also. So just a bit of a warning, for the next however many slides, I'll talk about things in terms of the Poincare inequality, but really the arguments will work quite generally for these phi Sobolev, and in particular for the log Sobolev inequality. Okay, so here is, I think, probably the most crucial one, is what I would call the tensorization property. And it's the following. So suppose that I have a bunch of probability measures which each satisfy a Poincare inequality with a positive constant, and I take the product measure of these guys. So independent copies. If you imagine the diffusion associated to these guys, it's n independent processes, each sampling from their invariant measure, right? So upon doing this, you can compute that mu will satisfy a Poincare inequality with a constant that is no worse than the minimum of these guys. Okay, and so from the level of the process, that's quite natural. You know, how quickly am I going to converge? As quickly as the slowest one-dimensional component. It's quite a natural argument. Okay. And so why is this interesting? It means you can, you know, once you have some Poincare inequality, you can really quickly construct very high-dimensional measures that you understand very well already, rather than having to analyze them from scratch. So I think this is one, you know, for some people studying concentration of measure, this is why these techniques are very interesting. And so if you're interested in those directions, I would recommend, you know, there's many good references on the topic, but I think a particularly excellent one is these set of lecture notes by Ramon van Handel at Princeton. Yeah, this stuff, it's useful if you just need to prove concentration inequalities, and for some people that's all you need. But actually the mathematical theory behind all this stuff is just excellent, and you really learn a lot from looking at it. I would say one reason I would single out Van Handel in this case is he does a particularly good job of emphasizing that you want to get bounds that don't depend on the dimension. Okay, that you take big products of things and things don't get worse. That's sort of a key feature in this area. Yes, okay. So another one that I really like is what I would call the transport method. So suppose that mu is a probability measure satisfying a Poincare inequality with some constant, and then let T be a Lipschitz continuous mapping. It doesn't have to be a bijection, but you should probably think of it as being a bijection, I would say. And suppose that it's Lipschitz continuous with constant L, and let pi be the push forward of mu under T. So I get a sample from pi by sampling from mu, passing it through this function. Okay. Now, if I take a test function f, and I define g to be the composition of f with t, then you see that the variance of g under mu and the variance of f under pi are the same thing, because it's the same random variable expressed two different ways, right? It's just, do I think of it as a sample that has already been pushed forward, or that I push forward as part of the function, right? Now, on the other side, we can look at this gradient norm. Because g is f composed with t, we can use the chain rule to pull out the Lipschitz constant of the transport map. We get this inequality here. Okay, so these are just elementary computations. And an immediate corollary is that your pi will now also satisfy a Poincare inequality with a constant that only degrades by this L squared, right? That somehow it's, you know, if you're a nice image of a nice measure, then you are still nice. And if the Lipschitz constant blows up, then things can get worse, right? So that's very useful. Yeah, and the sort of general idea of doing constructive Lipschitz transport, I think it's one of the most exciting things for me to read about these days. It's very active. You should think of it as being related to the optimal transport problem, but actually quite distinct, okay? It's distinct in the sense that in optimal transport, you are trying to couple two measures so that you don't move very much, right? Here, you're trying to move things sort of quite smoothly. It's there's a sort of a slight distinction there. That you would maybe say, I'm happy for the transport to move things more as long as it has a good Lipschitz constant, or something like this. And so actually the best ways of constructing Lipschitz transport maps that I'm aware of, they don't use optimal transport. They use sort of what I would call heat flow methods. Okay? And so this construction, as far as I know, was sort of introduced by Kim and Millman sort of 10, 15 years ago. And then since then, it's been greatly advanced by Dan Michelunter and Yair Schoenfeld. And they have this one paper and also several others that explain things very clearly. They both have many talks about it online as well. So if you find this stuff cool, I would definitely check those out. And here's another more recent paper that is also a very good read. I will share the slides and you'll see all of this stuff. One thing I'd like to say is that there are sort of some interesting and surprising links between these heat flow methods and diffusion models and sort of deterministic transport maps. They're sort of very closely connected. Okay. So here's a micro application that I can sort of do in one slide that combines these techniques I've already described. So suppose I have a bunch of independent random samples from probability measures that each individually satisfy a Poincare inequality with some constant, and I just take the sum of them. Okay, and you can average them if you like, but it doesn't really matter. You can directly show then that the law of this sum, which might be difficult to describe directly, it will satisfy a Poincare inequality with a constant that you can describe explicitly. And what is the proof? I'm sweeping details under the rug, but essentially the idea is you take these separate measures, you put them together by tensorization. They now live on the same probability space. And then you take the function that maps this vector of things to their sum. That's a Lipschitz transport, and you can go home. Okay, and so this sort of gets you, many other applications sort of directly. And this is sort of the spirit of things, is once you've proved these general principles, things become quite easy. Okay, another. Yeah, it's really a sum. Yeah. Right. Here's another one which is not always quantitatively fantastic, but in some applications it's really the right thing to use. So suppose I have another nice guy with a good Poincare inequality, and then suppose pi is another probability measure which is sort of mutually absolutely continuous in a strong sense, in the sense that the density ratio between the two of them is bounded well away from 0 and from infinity. Okay? Then you can show that this measure will itself satisfy a Poincare inequality with a new constant, where the way things degrade, it's to do with the sort of aspect ratio of this density ratio. It's max divided by its min, more or less. Okay, and so what's the proof sketch? It's kind of similar to before, right? We use a sort of quite elementary argument to relate the variances under the two measures, and similarly to relate the gradient norms under each of them. And this one here is particularly easy to see, right? You sort of write this as the expectation under pi of d mu d pi times the gradient squared, and then you upper bound that uniformly. Okay, so why is this a bit nice? So you could have that your mu is very smooth and Gaussian and whatever, and by doing this bounded change of measure, you could get something quite rough, right? But from the point of view of the Poincare inequality, you are not bothered by this. It's just bounded, and so things don't change so much. And that's something which I think would be much harder to show with a pathwise approach, for example, where the process itself could change quite a bit. Okay. A slightly more particular and recent one, where I'd say the heavy legwork was done in the past 5 or 10 years, is to look at mixtures, right? So suppose I have a family of probability measures indexed by x, each of which satisfies a Poincare inequality with the same constant. And all of these probability measures overlap decently, right? The chi-squared divergence between any two of them is uniformly bounded above. Okay, in the paper they have some sort of weaker assumptions than this, but it's qualitatively saying they overlap well. Then, if you take an essentially arbitrary mixture of these guys subject to that condition, then that mixture, so I pick a component x and then I draw from it, that will also satisfy a Poincare inequality, and the constant will only depend on the Poincare constant of the constituent measures and this sort of overlap parameter here, and in particular you don't see the dimension, which is again sort of important for applications. Yeah, I could have been saying this throughout, but all of these things are also true for the log Sobolev inequality for largely analogous arguments. Okay. So those are the sort of transfer principles that are particularly easy to teach. I think they're all quite neat. There's a few other routes of proving these inequalities that I can whistle through now. I won't go into quite as much detail for any of them, but they might be appealing to you for various applications, so I wanted to give a character of what's possible. Okay, so if you're someone who likes coupling, and I'm someone who likes coupling, one particularly appealing thing is to say, okay, perhaps I have some nice coupling of my Markov processes which contracts nicely in space. Does that buy me anything in the world of Poincare and log Sobolev, let's say? And so it's reasonably well known from at least the 90s and potentially quite a bit earlier that if you have what people would call positive Wasserstein curvature, so you can contract things on average, right? Then if you contract like 1 minus gamma in that sense, the same is true for the Poincare inequality. So if you're contracting in space, you're also contracting in L2. Okay. Now, if you also have that the process is non-expansive in the following sense, right? That wherever I am, I can couple draws from the kernel such that you don't go any further apart than what you started with. Okay, and that has to be an almost sure statement. That's why it's a T infinity. Right, so if your process can be made non-expansive, then you immediately get the log Sobolev inequality as well, which is quite a bit stronger in this case. Okay, so that's a slightly strange assumption, but I'll sort of explain why it's necessary in a moment. And actually, you can even accommodate a little bit of expansion, but it's harder to give the statement there. Okay, so with no additional conditions, if you have contraction, you get the Poincare inequality. And then if you also have some sort of non-expansivity in the worst case, you can upgrade that to contraction in relative entropy. And that's a very recent development, I should say. And so having done this, there's an argument that, okay, if you're interested in the strongly log concave setting, you can really solve it very probabilistically. You can do these coupling arguments and then use these general results to say you get the Poincare inequality and the log Sobolev inequality essentially for free. What's also worth mentioning is that if you're prepared to be a bit creative with the metric you have contraction in, you know, and warp it in one way or another, you can solve other cases where you don't have global convexity, right? And so this was done in the 90s by Mu-Fa Chen and Fengyu Wang, and then I think brought into a lot of prominence maybe 10, 15 years ago by Andreas Eberle, who really pushed this very far to show that for probability measures that are, say, log concave outside of a ball and not too crazy inside of the ball, you still have a spectral gap with a decent constant, okay? And Pierre Monmarché was also here last week. He's done things in this area as well that have been very impressive. Okay. So yeah, if you're interested in these directions, so the fact that contraction implies the Poincare inequality, this has been known for some years, particularly in the sort of Chinese probability school, centered around Mu-Fa Chen and Fengyu Wang, and also Li-Ming Wu. So these are sort of quite big names who, to some extent or another, did come over to Europe and have quite some impact here. The extension of getting the log Sobolev inequality under just the contraction assumption, this was conjectured to some degree or another by Perez and Totali, and it was recently resolved. This is really in the past 12 months, let's say, by Pietro Caputo, Justin Salé, and Florentin Munch. They show that you need this additional L infinity type contraction to get it to happen, and Munch actually is a very interesting sort of example of a Markov chain on 3 states, which has the contraction but not the L infinity contraction. And so it satisfies the Poincare inequality, but not the log Sobolev inequality. And it's just a little bit peculiar. But when you work on this stuff, this sort of curvature lower bound thing shows up time and time again. And so it's sort of worth learning about eventually. So let me click through. So this is where it's resolved, February of this year. Right? So that's a really nice development. Yeah, so the contractivity assumption, it gets you the Poincare inequality, but it also gets you various other things. I think if you want to learn about that, I would read this JFA paper by Jan Olivier, sort of what got me very interested in this topic. And then there's sort of earlier work from the turn of the millennium by Gelou, Guilan, and Wu that sort of pushes this direction in other ways. And I think it's sort of a very nice reference to get started with. Okay, and that's Chen, right, who was remarkably influential. He was Fengyu Wang's supervisor as well. So I'll talk more about Wang later. Okay. So I told you about this strong log concavity setting and said that's sort of a bit deficient because you could have curvature degenerating at infinity or something like this, and you would cease having interesting results. So it's natural to look at the following case where you still have convexity, but it's non-uniform, right? So we have some function rho of x where we have this pointwise lower bound on the curvature. It's still non-negative everywhere, but it's not uniformly bounded away from 0. So you can imagine a case of your potential is square root of 1 plus x squared, right? It gets very flat in the tails, but it doesn't go all the way down to 0. So there's a nice result of Besser, who shows that under this assumption, you enjoy a spectral gap, which is at least the harmonic mean of the curvature, right? So we've gone from the worst case curvature to the harmonic mean, which already enables some new applications. It's natural in many ways to try get this gamma all the way down to just the average curvature, but it turns out that this is not true, okay? You can sort of construct things. In a way, the simple proof is that in one dimension, every probability measure has positive average curvature. So, and we know that the Poincare inequality doesn't hold for every probability measure, so that cannot hold in general. There's also recent work of Catio, Guilan, and Fathi who sort of look at the same setting and try to refine things a little bit, but it's a bit less clean to state the results, but it's still very nice work. Okay, so here's one which will hopefully resonate with some people in the audience. So it's quite well known that if you're looking to prove exponential ergodicity for a Markov chain, you can use the so-called drift and minorization conditions, sort of pioneered in the early 90s by Mine, Tweedy, and co-authors. So what one does here is you assume you have some sort of function v, which is bounded away from 0 by 1, let's say, which under the dynamics of the process, this function contracts up to some point, right? So you see here that you'll quickly get to a region of the state space where v is at most k over gamma up to some constant. And so what you say is on some sort of set that I'm going to reach quickly from this drift, I have a minorization condition that any two processes who enter that set can be coupled with some probability, okay? So it's also well known that whilst this is a pretty nice strategy for getting exponential ergodicity, in terms of quantitative bounds, it can be a little bit poor in some cases. That's not a uniform statement, but maybe an empirical one, right? And so one hint at why this might be the case is that when you're doing these strategies, there's no natural way of doing tensorization that I'm aware of. That if you sort of take two processes which each satisfy a drift and minorization, and you look at the sort of product process, to say that this one will be, again, no worse than the worst of the two is not something I've seen explored so much. But I should warn that I don't know that side of the literature quite as well. Okay, so what is the culprit? Why are things not working quite so well? It's not the drift, it's the minorization condition, which gets more and more demanding as you move into higher dimensions. Okay, and so there was another perspective that cropped up, I think around 2008, at least that's the earliest reference I know, of a number of French authors who you'll see on the next slide, who took a new perspective. They said, keep the drift condition. The drift condition is a good one. Getting into the middle of the space, we all agree that's something that Markov chains will do, right? But instead of saying the minorization condition, which is that when you get into the middle of the space, you meet in one step, you say, no, I look at the process and its restriction to this set, and I just say that that process converges quickly, that it has what I would call a restricted Poincare or restricted spectral gap inequality here. It's sort of not exactly that because you have the variance under the restriction of pi to this set over here, whereas you can have just the full pi on the right-hand side. But qualitatively, one should think of it as that way. So you're just saying, once I get into this bulk, I am mixing quickly there. Okay, and that's sort of reasonably likely to hold because that will be a compact set, and things tend to not go so poorly on compact sets. So this strategy, as compared to drift to minorization, it seems that it can actually yield pretty reasonable estimates in the sense of being, say, polynomial with the dimension, let's say, which is much more challenging with minorization. They're not excellent estimates. They're not as good as we know they should be, but it's sort of a step in the nice direction. And I'd like to point, so there's work from 1 or 2 years ago by Tagvaye and Mehta in the US, who sort of brought this story full circle by taking the proof strategy of these French authors and combining it with the drift and minorization conditions to get a nice spectral gap estimate in that case. Okay, yes, so just a bit of an overview of this stuff. So this is the first paper that really did it as far as I know. So it's by Bakri, Barth, Catio, and Guillon. And so it's called A Simple Proof of the Poincare Inequality, and it is exactly that. The paper is very short. And actually, if you look carefully here, right, the paper was submitted at the end of November in 2007, and it was finally accepted about a month later, or 2 months later, in January of 2008. So it was simple enough that they sort of waved it through very quickly. And so that, I think, is very nice. So they use it to get the Poincare inequality, but actually if you push the strategy a little bit further, you can see that it applies more generally. So if you're prepared to make a stronger assumption than a geometric drift condition, then you can get a result which is stronger than the Poincare inequality. Or if you want to make a sort of subgeometric drift assumption, you can get subgeometric convergence rates and other things like that, right? So here's sort of how you do it for the better than exponential case through what's called a super Poincare inequality. I'll touch on that later. Here's a paper that sort of develops how to do the subgeometric case very well. I spent a lot of time reading this one and have a lot of love for it. They sort of do even more than just L2 type inequalities here, which was very useful for us. There's also, so this is lecture notes from the LMS, and one of the chapters in here is called Functional Inequalities by Lyapunov Conditions, by the two guys who really push this stuff as strongly as anyone. So any of those references are a great starting place. Maybe I would start with this one. And so that's Catio, and that's Guillon. Yes?
What they assume a drift condition?
So you have a drift condition, and then, yes. Sorry, I didn't say that, but you get a good estimate on the Poincare inequality for the whole process. Yeah. And you can imagine the argument, it's how long does it take me to get to the set? How quickly do I mix while I'm in the set? At a very coarse level. Right, so those were sort of the cleanest stories I could tell in a way. Here are some miscellanea which are a bit useful to know about. which I'm perhaps not as expert on. Okay, so there's this paper of Roberts and Tweedy from the late 90s, where they say that geometric L2 and L1 convergence are equivalent for reversible Markov chains, which is the case I'm talking about. They're not just equivalent in principle, but they're quantitatively equivalent as well, right? If you know a rate of L1 convergence and someone asks you what is the rate of L2 convergence, you already have an answer for them. And so that sort of says if you have any way of proving L1 convergence, then you can get a spectral graph out of that with no extra work. That's kind of nice. There's also these so-called localization methods built in the sort of early mid-90s in the computer science community, so particularly by Ravi Khanna, Laszlo Lovac, and Miklos Simonovits, and it sort of has been given new life in the last 10, 15 years through what's called the stochastic localization method, sort of a development of this older technique. There are also nice sort of symmetry arguments where if you're prepared to make structural assumptions on the target, some things become a bit nicer. Right, so if you work with a target which is sort of symmetric under reflecting each coordinate, that's called an unconditional log concave measure. And in that setting, you can prove some quite nice things. So there's a reference here by Frank-Barth and Boas-Klartag, which sort of pushes that quite nicely. There's also another very natural thing to try is to look at spherically symmetric log concave measures. And so Sergei Bobkov, Nolwenn Hui, and Kachoggi, Lan, and Wu also have some nice papers in this direction where they show, okay, if you're prepared to make these structural assumptions, you can really get quite a bit more. And again, you might naively say, I'm not interested in spherically symmetric problems, but that's when we go back to the transfer principles, right? If I can prove something nice about a spherically symmetric measure and then transport it to the thing that I actually care about, then I've got something, right? So somehow there's this whole ecosystem of inequalities that sort of fit together quite neatly. Okay, so that was a little bit about how to check that the Poincare inequality and to another extent the log-Sobolev inequality hold. Once we have them, what do we do with them? So I've told you, you will get L2 convergence of the process or entropic convergence of the process. There's a few other nice things that I think are worth knowing. So what are some implications of the Poincare inequality? So so we write it up like this, right? That the variance is upper bounded by the Dirichlet form, and I'll write C for the covariance matrix. Now, by taking linear test functions in this inequality, you can see very quickly that if you scale the covariance matrix by gamma, it is dominated in the semi-definite ordering by the identity. So if you have a big Poincare constant, you must have a small covariance matrix, okay? That's sort of a direct consequence. And so there's a very famous conjecture in convex geometry called the KLS conjecture. That's Khanna, Lovac, and Simonovits from the previous slides, saying that actually, if your probability measure is log concave, you can reverse this inequality, more or less. That you compute the operator norm of your matrix, then there's just some universal constant, doesn't depend on dimension or anything, that gives you a lower bound on the spectral gap. So this is really specific to the log concave case, right? And so what is the interpretation? It's saying, from the point of view of L2 mixing, if you're log concave, what is going to stop you from mixing quickly? And it's saying qualitatively, the only thing is getting from one side of the distribution to the other one, right? That's sort of what the operator norm is telling you there. Okay, and so from the algorithm's point of view, this is sort of proven, right? So in the past couple of years, Boas-Klartag has proved it, where CKLS is sort of very weakly dimensional, sort of square root of log d. And so if you're interested in polynomial time algorithms or even the right polynomial exponent, you're done, right? But it's still mathematically interesting to push it forward a bit more. So there's been sort of a flurry of research on this in maybe the last 3 or 4 years, catalyzed by a breakthrough result of Yense Chen, who's at ETH now, and then Klartag with Joseph Leek got it to log d to the 10 or something like this, and then he finally refined it to this square root of log d. And it seems plausible that it will be completely proven within 10 years, but you never know, right? Okay, so again with the Poincare inequality, remember how it looks. If I take a Lipschitz function g and I take its exponential as such, so I can do a sort of simple inductive argument where I bootstrap the Poincare inequality to show that the moment generating function of g is bounded like this. Okay, that's a nice exercise to go through. What it tells you is every Lipschitz function will have sub-exponential concentration, sort of lighter than exponential tails. Okay, so that tells you something about the shape of the measure in a way. And so because we know that the exponential distribution satisfies a Poincare inequality, we can't expect better in general, right? Poincare says you have lighter than exponential concentration and possibly better, but not provably better. Okay, now let's do the same program for the log-Sobolev inequality. Again, writing it in this way, we can take sort of exponentiated linear test functions to get this inequality here, sort of a simple calculation to do. And so there's a paper from a year or two ago by Pierre Bizel, who makes a sort of analogy to the KLS conjecture, saying, if I have a similar estimate on the moment generating function of this sort of quadratic form, then I have a log Sobolev inequality, and the constant is lower bounded in this way. Again, it's the same story. Under log concavity, the only impediment is getting from one side to the other, because we know there's no other bottlenecks somehow. Similarly, you can do the sort of exponentiated Lipschitz function idea, and there's what's known as the Herbst argument from an unpublished argument of Ira Herbst in the 80s, I want to say, shows that any Lipschitz function will have sub-Gaussian concentration properties. That's very useful in practice, sort of very widely used in machine learning and statistics, I would say. And so again, we get a consequence of this is that pi has lighter than Gaussian tails, right? Or at least as light as Gaussian tails. And because the Gaussian satisfies this inequality, we can't hope for better than that. So Poincare means sub-exponential, log Sobolev means sub-Gaussian. And you could be better, but you don't know it, right? So I'll wrap up this section quite soon. So another implication of the log Sobolev inequality is, so the basic inequality shows that the entropy is contracting over time. So the same quantity is shifting and shrinking. But actually under the LSI, you can get something a bit remarkable, which is you can start with a function which is, say, L1 integrable, and after evolving it under the flow for a little while, it can become L2 integrable, and L4 integrable, and so on. So the sort of tails are really contracted quite strongly. And so this is what Nelson called hypercontractivity. And so this is sort of the specific formulation of it. But the point is you start with something which is in LP, and you end up with something which is in LQ for a Q that's much bigger than P. Okay, and so this is qualitatively related to the fact that your process can converge very quickly at the start somehow, and then slows down to linear rates. And actually, one can show that whilst the log Sobolev inequality implies this, it also goes back in the other direction. If you have hypercontractivity, you necessarily have the LSI as well. Okay, there's some sort of related inequalities which I can click through, but I think in the interest of time, it's good for us to take a little break now and start again at 5 past the hour. Yeah, okay, so thank you. Sure, yeah, we can take a little break. I'll just click through these silently for the online audience. I think so. Okay, there we go. Yeah. Yeah. There's, sorry. Can I tempt you?
What are these?
So these ones are chocolates, and these ones are sort of more rubbery sweets in a way.
Well, I don't mean to take all of that, but I want to open this.
Please. Yorgos, can I tempt you? Let me, Now, I looked it up, and apparently Starburst and Skittles are pretty reliably vegan friendly, which is the thinking. Wow. Yeah, it's not a surprise, but
Yeah.
Tour de force. Very nice. Thank you for putting this in.
oh, that's okay. I'm glad that I baked in stuff that I could skip,
What do you mean?
as in the last 5 slides or whatever. It's like, oh yeah, that's fine to leave.
But I mean, some people have superpowers, but after a certain point, you start to remember only the main
Yeah.
messages, right?
Exactly.
There's a micro, not so big. Oh, yeah.
Please help yourself.
No. Yeah, I asked him. Moment to breathe.
Until 5 past the hour, so another 3 or 4 minutes.
Can this technique be used for the following? So you have backward Kolmogorov equation of semigroup.
Mhm.
Possible to prove that in the very case, using this technique, that derivatives should be kind of related to the flow of derivatives of the semigroup
In T or in X?
is exponential.
In X?
In both.
Okay.
Is exponentially decaying. Well, in T is easier. But
Yeah.
in space. Because if you have in space, then it automatically happens.
Yeah. So this Bakary-Gentile-Ledoux book I talked about, they have that in there.
In
So-
the convex case.
So in the strongly long concave case, you definitely have contraction of the gradient, let's say.
And they prove it through this technique, not PDE technique.
Yeah.
Because there are proofs from PDE techniques with embedding and so on, but this requires it.
Yeah. So there's another work of Kawada, I think, and it's something like if you can show that your process of almost any metric, let's say, a nice enough metric, if you have LP contraction in that metric, then you have LQ contraction of the gradients in a way.
Well, gradients, we need more than typically than that, so we need kind of
Higher gradients. So yeah.
Hessian, well, ideally for derivatives.
Okay. Yeah, I can think of things that might work, but
Because this is used for convergence of numerical schemes.
mhm.
So to get this constant independent of time, so this is
Yeah, that makes sense.
they rely on Sobolev embedding of that and it's horrendous.
Yeah.
In a way. Also they're very, because it is PDE, it's very specific to a problem.
Yeah.
So as soon as you change a bit the problem, you need different proof.
Yeah, that makes sense.
Plus Sobolev embedding because it's dimension dependent.
Yeah.
The higher smoothness you need, the higher. So basically, you need infinite smoothness. Because if your dimension is whatever,
Yeah.
then the smoothness should be, which doesn't look sort of right.
Mhm.
Because the solution of backward Kolmogorov equation itself, you don't need infinite smoothness.
Yeah.
Okay, so people are working using.
Yeah, so yeah, it is more work, and it's definitely nicest in the strongly long concave setting. But the expectation would be there will be a more general version. Yeah.
PDE stuff was used first, I think, by Daniel Talay.
Mhm.
Tony, Gabriel Stolz.
Yeah.
So they also use DD technique.
Yeah. Okay, let's see here. Okay. Sure. Okay, I'll get started with the second part of the presentation now. The slides are a little bit less refined for this one. I think I'll take it easy, and if I don't say everything I need to say, then it's not the end of the world. Yeah, you can see from this that we're sort of making a transition from the very smooth and continuous world to the more discrete setting. So let's click through. So yeah, we're going to talk now about discrete time Markov chains, or somehow using functional analytic techniques for, practical MCMC in some way or another. Okay, so some of what we've done so far is quite particular to the setting of the Lange diffusion, but luckily a lot of the setup is quite general if you cast it in the right language. Okay, somehow, some of the things, it really relies heavily on the fact that this squared gradient term is appearing. But some of it makes sense for general Markov chains with a more general notion of Dirichlet form. Okay, so I'll sort of try to elucidate that here. Throughout, I'm going to work with a Markov kernel P, which is pi reversible, and as Joras clarified, sort of spectrally positive. And what that means is, if I look at the Markov chain from one step to the next, any function of that Markov chain is positively correlated. I'm not magically having anti-correlations somehow. That's something you can easily cook up with sort of standard tricks. Also, because I understand it best, the goal here will be to look at the L2 or kind of Poincaré picture here. The log Sobolev stuff will not get quite as much airtime. And I'll give a hint at why that should be the case. Okay, so we sort of used Gronwall's inequality to try construct functional inequalities in the diffusive case. We're going to talk about that briefly here. So yeah, as before, we want to show we have some sort of contraction of some norm or some entropy. So one reasonable goal is to say, okay, let's look at all of the functions f that have mean zero at equilibrium and show that the semigroup contracts them from one step to the next with some constant gamma. Okay, and if we have this, then through stuff that I described before, we'll get nice long-time convergence guarantees for the process. So if you square both sides and expand things out and shuffle them around a bit, this will turn out to be tantamount to the claim that a certain interesting object over here, which will be correlated to this Dirichlet form that I talked about before, upper bounds the variance of the function, right? So before we had sort of the squared gradient norm over here. Now we're going to have something a little bit different, which is well adapted to the specific setting that we're looking at. And so what is that going to be? So in the general setting, let T be a Markov kernel, which is still pi invariant. It might be P, but it might be something sort of derived from P. Okay, and so we're going to say, look at F, look at the identity operator minus the transition density applied to G, and then integrate the product of these with respect to pi. Okay, so it's related to this, F and minus L of G from before. And concretely, when you sort of do a bit of shuffling, it's the integral or the expectation under this measure here of this quantity here. So what is this measure? This is I draw X from the equilibrium distribution, and then I take one step according to the Markov chain. Okay, and so what is this delta f of g? It's I look at these functions f and g, I see how much they change from one step to the next, and I take the product of them. Okay, it's qualitatively a very similar object. So for these chains that we're going to be talking about today, this Dirichlet form, whether I take t to be p or this p star p that I mentioned over here, so p star is the time reversal of the kernel. For us, it'll be the same thing as what we started with, right? These two things are directly comparable up to some universal constants, so we may as well study whichever one is more convenient, and will almost always be the first one. Okay, so we're going to study this object with t being equal to p, sort of suppressing for a moment that we will eventually use it with t equal to p star p. Okay, and so it's again sort of, how much are things changing from one step to the next at equilibrium. So how does this relate to the diffusion picture? Because a priori I've just given another definition. Maybe it has nothing to do with anything, right? But what is actually true is the following. So let t be greater than 0, and let pt be the transition kernel for the diffusion run for time t. So that's now a discrete time process, right? I'm just time sampling the chain. So as t goes to 0, you can look at the Dirichlet form as I've just defined it for pt, rescaled by the time. And as you send the time to 0, it looks exactly like this. You can do it by Taylor expansion or pathwise as you like, but it's suddenly true, maybe up to a constant, but I think literally true. And so what is the sort of idea of the proof? So, in the definition of the Dirichlet form, we have the identity minus the kernel, right? So in that case, it's going to be the identity minus the semigroup. How did we define the generator of the process? Precisely as sort of this thing divided by t in some limit. And so to sort of, first order, this is true. And that's the moral structure of the proof, if you like. Okay, and so this says we have genuinely generalized the picture we had for diffusions. We haven't just come up with some new definition. It's sort of all consistent and will fit together nicely. And so whereas our Poincare inequality used to be upper bound the variance by the squared gradient norm, we're now going to upper bound it by this object here, right? Which is natural enough. It's a much more sort of finitary rather than infinitesimal object. It comes with new challenges, but we will be able to control things in some cases. Okay, so are we back to square one? Or can we use the stuff we've proved already to some extent, right? So it's instructive for us to revisit these earlier principles and transfer and so on, and to assess what remains. And so, I don't expect you to have memorized the arguments I told you before, but I'll tell you that, the tensorization argument works completely as before. And, it's the same idea. If I have independent Markov chains, how long does it take for the ensemble to converge? As long as the slowest one. I don't care whether it's a diffusion or anything else, as long as they're independent, right? So we still have tensorization. The bounded change of measure argument, it goes through exactly as before, right? The process sort of changes in some sense in that case, but I'll show that more explicitly later. And the mixture argument, which I didn't actually show in detail, that also goes through. So these are sort of, abstract constructions that use measure theoretic generalities, not the specifics of a diffusion. And that's very useful for us. You'll see that the transport one is not here, right? The transport is somehow a very specific thing. To talk about a Lipschitz transport, you need metric structure, for example, which a Markov chain might not have, right? It's asking a little bit more. So I talked a little bit about metric contractivity, right? So if I had my diffusion contracting exponentially in some transport distance, I could get the spectral gap estimate. That's still true here. Okay, so that's very nice. This sort of typical curvature I gave with the harmonic mean, that is not necessarily proven in this generality, but it's quite plausible that it will still hold. Okay, so there's some sort of flexibility there. And also these Lyapunov arguments of Katio-Gilan and co-authors, these also go through in the discrete case. You have to shuffle terms around and do a bit of bookkeeping, but the core idea definitely still works. So when do we lose something? The general rule of what to expect is that if to prove the result, you use the chain rule at some stage, you use some sort of very calculus type stuff, then that can be a bit of an impediment, okay? So that's not always the case, but for some things it's true, and I think I'll give an example now. So let's go back to the logarithmic Sobolev inequality, which I said you could write in two different ways, right? So one of the versions was you upper bound the entropy of f squared by the squared gradient, right? So a generalization would be say, okay, replace the squared gradient by the Dirichlet form. That's one option. But we also had this one where it was the expectation of grad f squared divided by f, okay? And so by the chain rule, that's the same as grad f times grad log f, okay? So we could easily propose the second one. Okay, that would also be a valid generalization of the log Sobolev inequality. So this one's equivalent to what in his talk last Monday, Giacomo Zanella called entropic contraction. So this is the one you get from sort of the discrete time Grandmol argument to say that you contract to equilibrium in KL divergence at an exponential rate. So what he proved about the Gibbs sampler was this sort of a statement implicitly. This statement up here, it's not immediate, but it follows from some elementary calculus that it's slightly stronger than this one, okay? So if this one holds, then this one holds. And so, yeah, in general, the former is strictly stronger. There are cases where this is true and this is not true. This is exposited nicely in, I think, a Stock paper by Markov and Totali from the early 2000s. What's a little bit interesting is that in some quite recent work of Justin Saleh, I think Konstantin Tikhomirov, and Youssef, whose first name I'm not sure of, they clarify some cases where actually you can go between the two of them for reversible chains. So it's not true in general, but there are non-trivial settings where you can translate between the two. But this is sort of a very simple example of, not having the chain rule on discrete spaces means that these two are not the same thing, and you have to be careful which one you use. Okay. So yeah, I should say, people would normally be happy to call this one a log Sobolev inequality, and they might prefer to call this one a modified log Sobolev inequality. But that term can kind of be used in many different ways, which is a bit fraught. So I think saying entropic contraction is sort of slightly more useful. Okay, so the main goal today is to give an idea of how these techniques are useful for Markov chain Monte Carlo algorithms. I'll give a few warm-ups, which I think they will seem very elementary, and they basically are. But they are pretty representative of how we end up using these things. Sort of quite simple tricks, but for a well-chosen comparison somehow. And so these are all going to be based on sort of MCMC algorithms that have this propose, accept, or reject structure. You propose a move, and you either go there or you don't, and possibly you do some third thing. And so the case studies I'll give, I'll go through these at a gentle pace. I think they'll be good for all of us. Okay, step one will be I take one of these algorithms and I see what is the difference between using the so-called Metropolis accept reject function and the Barker accept reject function. That's a nice simple one. Another one will be to revisit this bounded change of measure thing, right? So if I'm doing random walk Metropolis and then I change my target gently, right? How will things change there? And then a similar thing for doing a bounded change of measure for the proposal kernel, keeping the target the same. Okay, so seeing that we can actually apply the same argument in different places of the Dirichlet form and get some nice results more or less for free. Okay. So, yes, and then there'll be some more serious case studies later, but we'll see how we go for that on time, and the slides for that are certainly not as complete. Okay, so we're talking about Metropolis Hastings type kernels in this section because it's a nice advertisement for how I use these methods, let's say. So what is the general protocol for one of these methods? So if I'm at the current location X, I propose a move to some location Y, which is drawn from this so-called proposal kernel Q. Okay, then I compute what I would call the sort of acceptance ratio, R of X to Y, which is this sort of density ratio object here. So the probability of being at X and going to Y compared to the probability of being at Y and going to X, something we can compute in practice quite easily in many cases. And so what we do after computing that with a probability alpha xy, which is a simple function of these guys, we move to y. With the remaining probability, we stay at x. Okay, so sort of well-studied methods and quite practically implementable. Okay, so we'll give some examples on what happens when we have this structure to the method. So what does the Dirichlet energy form look like in this case? It's not going to be a gradient. We're moving very discretely and quite slowly in comparison, perhaps. So in this paradigm, you can compute quite explicitly, and it's a really good exercise to do. The Dirichlet form writes as follows. So the energy between f and g is I sample from pi, I sample from q, so that's my proposal. I add in this weight here, which is my acceptance probability, and then I have this delta as before, the f of x minus f of y, and so on. Okay, you might think that's a bit strange. There's no term there for when you reject the move. Right? You sort of only keep this part of it, but of course that's to be expected because in those cases this term would be 0 anyways. Okay? And so what's nice about the Dirichlet form approach for Metropolis Hastings algorithms is that the sort of accept-reject structure is smoothed out quite a bit. You only look at the nice part of the objective. Okay? So it's not a separate term to worry about. You don't have to do a case-by-case analysis. It's just this is the object. I quite like that. Okay, so some warm-up applications. As I said, these are perhaps a little bit interesting, but mostly they're here to illustrate the tricks of the trade and the sort of manipulations that one makes when doing these comparisons. So qualitatively, you'll see that they're very similar to these bounded change of measure arguments I was talking about before, which in the diffusion context, well, actually, yeah, in the classical context, let's say, people often call this the Holly-Struck argument, after Richard Holly and Daniel Struck, who did this for sort of easing models in the late 80s, I think, but it's sort of taken on a life of its own. Okay, and so the emphasis is not that I'm proving really remarkable things, but that this same trick can actually be applied in a few different places and lets us compare algorithms that are not necessarily so easy to compare in a pathwise way, let's say. Maybe one point I haven't made yet is, when you're doing these analyses, you're never it's sort of implicit, but you're never really thinking about a trajectory of a Markov chain. At any given time, you're thinking about the first step and the next step. And if you can understand that, you understand everything, right? And you can sort of see why, being in the reversible case is well suited to that. For sort of processes with more ballistic behavior or this sort of thing, the sort of multi-step behavior is more important in a way. Okay, so let's sort of walk through some examples, do some nice calculations. So what I do, I fix my target distribution pi, I fix my proposal kernel q, but now I'm considering, I can accept moves in one of two ways. So one would be the so-called Metropolis-Hastings rate, which is I take the minimum of 1 in this ratio from before. That's valid, that will give me a convergent algorithm. I could also do what was proposed by A.A. Barker in 1964 and use this different function, this rational function r over 1 plus r. Again, it's increasing, bounded between 0 and 1, and so passes those checks. And you can check sort of explicitly that this will again generate a pi-reversible chain and it's fit for purpose. And actually that you can sort of consider some slightly more general things here, which are interesting in different contexts. But okay, so these are two things you could do. How should we choose between them, right? Why should we prefer one to the other? And when might we change our mind, let's say? So I should say there are some cases where you can't implement this and you can implement this. They're a bit peculiar, but they do exist. Okay, so let's do some painless verification. So here are the two functions. What do they look like? Draw them up. So here's R, and then here's 0, 1. So the Metropolis function is the minimum of 1 in R. So it looks like that. The Barker function, r over 1 plus r, sort of increases more slowly, like so, eventually asymptoting to 1. And then if I sort of halve the Metropolis function, we see that because this guy is concave, it's going to sit below, right? So I can draw that line there. That's alpha mh over 2. Okay, so that's proof by picture. You can prove it 6 other ways if you want to, but it's definitely true, right? Okay, so why is that useful for us? Well, let's go back to the Dirichlet form momentarily, right? If I go from one alpha to the other, this doesn't change, this doesn't change, this doesn't change. This is the only guy that changes. And I'm saying I can sort of sandwich them in between themselves. And so what do I get from that? Is that if I look at the Dirichlet forms for the Metropolis and for the Barker acceptance functions, you can order them in this way. Okay, and so by comparison with the diffusion case, bigger Dirichlet forms mean faster dissipation of entropy, faster convergence to equilibrium. If this guy is bigger, then we're happy. So what does this say? This says, if I just look at this inequality here, all other things being equal, if it's the same effort for me to implement each of them, I should always prefer the Metropolis, right? And this sort of Barker approach is never going to be better, again, other things being equal. Some people would call this a sort of Peskin ordering type result, related to a work of a student of Wilfred Hastings, Peter Peskin. Now, looking at the other side, we see that things are not really so different, right? That the Barker approach is at least half as good as the Metropolis-Hastings approach. And so if someone forces your hand and you have to use the Barker approach, you don't lose too much. You're losing a factor of 2. And it might be, for very boring hardware reasons, one might be more interesting than the other, and you don't have to lose sleep over it, okay? They're sort of completely acceptable in that way. A nice little exercise you can do is, so I said here, if I have a general function beta, which satisfies this so-called balancing condition, right? Then this is quite easy to construct in practice, right? Then it will also give you a valid Metropolis type algorithm. And you can show in these cases that you will always have under some sort of natural conditions that they're sort of increasing and bounded in the right way. Like so. Okay, so you can always lower bound whatever balancing function you use by the metropolis balancing function times its value at 1. Right? And so this would give you a similar result here as well, saying, okay, how much are you losing? You're only ever losing as much as you're getting up at r equals 1. Basically, so that's a nice explicit calculation. Okay, so that's changing the acceptance function. Now, let's click through. Here's another simple one. So fix the target, use metropolis acceptance rates, because we agree that's probably a good idea. Now let's see how to choose between two different proposal kernels that are sort of qualitatively similar to one another. You can think I have a random walk metropolis, and I say, what if I inflate the variance of the proposal a little bit? Okay, and suppose that they're each symmetric. This will mean that the acceptance probability doesn't see Q anymore. It just looks at the difference between pi, which is nice in various ways. Okay, and so suppose that these two kernels are similar to one another in the sense that uniformly in x and y, you can upper bound the density ratio between the two of them, below by delta plus and above, sorry, below by delta minus and above by delta plus. So in a way, you can view this as saying, you know, the left-hand side is saying the tails of Q2 are at least as heavy as those of Q1, and there's a similar statement that describes what's happening on the right-hand side. Yeah, in practice, it might be interesting to study cases where maybe this is finite and this is infinite, or vice versa. But I give you the result and you do what you want with it. Okay, so under this assumption, again, just using the Dirichlet form approach, you can compute directly. The Dirichlet form of the second proposal is sandwiched between these multiples of the Dirichlet form of the original proposal. Okay, so they're sort of comparable. If you only change the proposals a little bit, then the overall convergence behavior doesn't change too much, modulo some details. Again, it might be harder to explain this pathwise somehow. You're just saying, I changed the densities a little bit, the course behavior doesn't change so much. One interpretation of this, if you have to sit with it to make sure you've got the inequalities going the right way, but typically one interpretation is that if you take a proposal and you make it a little bit more heavy-tailed, it can't harm things so much. You're sort of seeing a little bit more of the space. Now, if you make it substantially more heavy-tailed, then these constants can blow up, of course, so you have to be careful. But that's sort of a nice little takeaway. Okay, and here's one that's a little bit more advanced, right? So here you should think of this as, I'm running random walk metropolis on two quite similar targets. Should I expect them to converge at similar rates? Okay, so I'm fixing some symmetric proposal Q, and I want to see what happens as I change the target from pi to pi prime. Okay, and so as earlier, I'm going to assume that the density ratios are uniformly bounded on both sides. And so to study this, we want to look at the Dirichlet forms for each of these different chains. Notice that two things changed now. So one is that we're integrating over pi and pi prime here, right? The Q stays the same. And the alphas, this is still an alpha in the classical sense, but I'm just highlighting that these will not be the same function. I'm going to be comparing different densities. Same deltas, these will be non-negative, so you don't have to worry about them too much. Okay, so where do we start here? Well, in essence, there's only two things to work on. How do we compare those terms? How do we compare those terms? In principle, you could study them correctly, and thinking about it for a moment, perhaps I should have. But anyway, you'll see what I've done, and the point is that it's easy to do it, and if you want to refine it, it will take you 12 minutes, let's say. Okay, so let's look at the acceptance probabilities first. So what are the acceptance probabilities for the modified target? It's like this, okay? And then I want to say, okay, I want to replace these primes by the unprimed versions, right? So pi primed of y is going to be lower bounded by pi of y times a suitable infimum. Similarly, 1 over pi primed of x is going to be upper bounded by 1 over pi of x times a supremum. And so we pick up a factor of kappa inverse here, where kappa is this sort of aspect ratio I talked about before. It's always greater than or equal to 1, okay? Just as a quick type check. So you have this here. We're already in good shape. Since it's greater than 1, we can pull the factor out the front, right? I mean, you could write min of kappa and 1, but you're just going to say that's lower bounded by the same thing. Okay, and so this is the acceptance rate that we actually care about. And so we get this uniform bound, right? For the modified process, the acceptance rates are always at least as good as those of the original process, scaled back by a factor kappa. Okay? Now, from that, it follows if we look at the Dirichlet form of P, right? I can take this pi of dx and replace it by pi primed of dx, picking up this supremum factor out the front. That's very easy. I'm taking the alpha and bounding it by alpha prime, picking up a kappa along the way. Now I combine them and I simplify this. Okay, so that's one step, is I've worked with the Dirichlet forms to make life easy. Now, with the same argument I showed you before, if I want to compare the variance under this distribution with the variance under this distribution, there's an elementary argument that lets me do it in terms of the supernorm of the derivatives. Okay. So what have we got? We've got a comparison of Dirichlet forms, a comparison of variances. We can put them together now. And so let's assume that our original process converges quickly. So the Dirichlet form for the Markov kernel P is converging to pi at a rate of at least gamma. So we can now say, okay, look at the variance of a function under pi prime. I can compare that to its variance under pi. Now, because I have this spectral gap inequality up here, I can introduce the Dirichlet form of P. Then, using the result from the previous slide, I can turn that into something involving the Dirichlet form of P prime. I collapse these terms together, so this will give me another factor of kappa, and I get a new bound here. So if I have a spectral gap of kappa for the original guy, then it is preserved up to a factor of kappa squared. And it's possible to get this, it might be possible to get this down to kappa with a marginally different analysis, but the point is that it's not so complicated to get this for something which would be quite a bit harder to treat pathwise. Right? I hope I'm correct about that at least. I wouldn't know how to do it. Okay, so those are the sort of more elementary examples, right? But these are kind of the tricks that we are routinely using in this area. These are the kind of perturbations we can accommodate quite easily. And you notice here that the precise details of what pi over pi prime looks like, they get washed out completely. If you know an upper bound and a lower bound, you know what you need to know. If you want a sort of finer answer, you can look at the tails or the moments or something like this, but you can be very agnostic to the fine details of the perturbation. Okay, so I will try, I think I have time for at least one of the more advanced examples I want to do. We'll see if I can do both of them. So the examples I want to talk about are to do with what people would call exact approximate Monte Carlo methods. Okay, so what does this mean, right? So we're in a setting where there's some standard method, maybe an MCMC algorithm, let's say, that we would like to run to sample from some distribution, but it cannot be implemented directly. Okay, so one example would be, in the Metropolis algorithm. Click back. Right, so if I want to implement a Metropolis Hastings kernel, I need to be able to do this proposal, evaluate this density, simulate this Bernoulli, right? And there are applications where it might be that this pi of y cannot be computed in closed form, even up to a constant, which is the usual setting we would have. Okay, and so there are settings where the basic algorithm actually does not apply, but there are sort of ways of simulating an approximation to the algorithm that behaves the way we would like it to. Right, so that's one example. Okay. So these tend to arise in problems where the standard method cannot really be implemented because there's some computational intractability associated with the model, let's say. And so the general sort of thematic idea is you identify the intractable parts of your algorithm and you replace them with some suitable Monte Carlo approximation, which is compatible with the usual structure of the algorithms in the way that we'd like. Maybe that you're still simulating from some consistent joint distribution, or you replace something you don't have with an unbiased estimator. There's sort of a bit of a rule book for how to go about it, if you like. So that gives you an approximate process, which should be close to the standard method if this Monte Carlo approximation is of a high quality, let's say. And I'll give some examples shortly. The important thing is that there are various cases where you can replace the truth with an approximation and get a new process that still has the right long-time behavior, okay? So it's not a case of, you add a little bit of bias at every step and things spiral out of control. Things really stabilize, and at infinity you have the right distribution, and so on. Okay, and so these methods can be of substantial interest for certain statistical models, and some examples beyond that, but I think sort of challenging statistical models with latent variable structures and unknown normalizing constants and so on would be maybe the standard use cases, let's say. Okay, so I will try, so the two things I wanted to talk about, and we'll see how far we get through. So probably the two first MCMC algorithms one learns about in a statistics course, they are the Metropolis Hastings procedure and Gibbs sampling, or conditional simulation, okay? And each of these admits an exact approximate formulation, which we can analyze reasonably well. And so if we're lucky, I'll be able to talk about each of them. But for now, let's just try to talk about exact approximate Metropolis Hastings. Okay, so what is the setting here? Is that we might have a model for which evaluating the density is not possible, even up to a constant, right? This is the typical case here would be that pi of x is the marginal of some higher dimensional distribution where you want to integrate out some other random variables. And that's not something we can necessarily do. There are settings where this is the case, but given a value of x, we can construct an unbiased Monte Carlo estimator of this density up to a constant, okay? And we might say, okay, once I've done that, let me plug that into my Metropolis algorithm and see if it works, okay? And so one way of formalizing this would be to say, and there's many choices for how to describe it, but this is the one that's mathematically nicest, is when I'm at x, I want to construct an estimator of pi of x. So what I'm going to do is I'm going to sample some noise variable w, which is non-negative and has mean 1. And then what I observe is not w, sorry, one sec. Okay. Thanks. So I draw this noise variable, and I don't observe the noise variable. What I observe is the product of this noise variable with the density that I care about. Okay, so that's sort of saying an unbiased estimator is the truth times something that has mean 1. Okay, that's the right formalism for this, in a way. Okay, and so what's nice is that when you set up the algorithm in the right way, if you go to your Metropolis step and you replace every instance of pi of x and pi of y with an estimator of this form in the right setting, you still get a Markov chain with the right long-time behavior. You preserve the invariant measure that you care about. So it's a very nice construction that Christoph was very much involved with. And so this is known in the literature as the pseudo-marginal approach, essentially because this pi of x is the marginal of some other distribution that you're sort of approximating. Okay, let's take our time. So we're still going to do a Metropolis type approach, but it's a little bit more complicated than before. So I just want to describe it quite explicitly here. So the state of the Markov chain is no longer just your position, but it's somehow also your approximation of the density at that location or the noise variable. It's equivalent to have one or the other, right? And so what do you do at each step? You propose a move to a new location y, and when you get there, you sample an approximation of the density at y, or equivalently, you sample the noise variable at y, which will be called u. So what we do is we compute this acceptance ratio, which instead of being pi of y q yx over pi of x q x y, we replace everything by its estimate, okay? And then with the sort of probability of min of 1 of r and of this, we make the move, otherwise we stay where we are. So it has the same structure as a usual Metropolis method, but there's sort of extra variables to carry around. Just a quick point is you really do carry around the previous estimate. You don't generate it afresh at each step. That would be a different algorithm, which typically doesn't have the right long-time behavior. Okay, so this is an algorithm you can implement in various cases, let's say. And so we want to study how this converges to equilibrium. One point is, we would maybe compare it to the actual Metropolis algorithm. That's a natural thing to do. But a challenge there is that that algorithm lives on a different space, right? This algorithm has an x and a w. That one just has the x. And so if we want to compare them, we need to synthetically re-inject the w into the original process somehow. So, I'll sort of write down what that means at the level of the Dirichlet form, but once you look at it for a little while, there's a clear thing to compare it to, let's say, which should reflect most of the behavior of the ideal algorithm. Okay, so this is a little bit dense, but let's pass it. Okay, so for this, this procedure here, I should have said it would be called a pseudo-marginal Metropolis-Hastings method. It's the Metropolis-Hastings with this sort of approximate of the marginal density used in place of the true density. So what does the Dirichlet form look like in this case? So when we write down the Dirichlet form, we start with the invariant measure. What are we converging towards as t goes to infinity? So we're going to have a pi of x. That's definitely what we want x to be drawn according to in the limit. But what is the distribution of w going to be? Yep. Oh, yeah. So it's not actually the law of this weight, but it's the law of this weight multiplied by the weight itself. And we see that because this has mean 1, this part will also integrate to 1. So that's a sort of bona fide probability. So this part here is the invariant measure. Then we have the proposal, right? Move from x to y, simulate the noise at y. then we have our joint acceptance probability and this same delta function from before. Okay, so that's the Dirichlet form for the pseudo-marginal algorithm. Now, the ideal algorithm is something a bit different. So we have the same invariant measure here. So it's sort of legitimate to compare them, let's say. And so the sort of algorithm you imagine yourself implementing is I move from x to y. Instead of sampling a weight from omega of y, I sample from this reweighted guy here, which is what the distribution it will have at t equals infinity. So I sort of sample a perfect weight, if you like. And then instead of using this more complicated acceptance formula, I just use the original one. Okay, and so if you look at a realization of this process down here, if you just look at the x, it will be the standard Metropolis-Hastings algorithm, and you're just carrying around this information with you as a sort of instrument. And I think these will even be sort of conditionally independent at each time, let's say. Okay, and so what we would effectively like to say is how does this relate to this? Okay, how can we compare the two? And so there's two things we might intuitively think. One is, by sort of a very loose analogy with the Barker example I gave earlier, I would say if you can implement the exact algorithm, then you should prefer it to this approximation. Okay, that's a nice sort of sanity check in a way, that by injecting this extra noise, you don't miraculously make things better. And then a second thing you could do would be to say, under what conditions is the process described up here almost as good as the one down here? Okay, and so you can imagine it should have something to do with the behavior of these weights and perhaps their tails somehow. So let me scroll back for a second. So, right. So you can see that so imagine x and w are fixed and you want to see how difficult it is to leave that state. Okay, it's going to be harder if this estimate here is a big overestimate of the true probability. Okay, that will mean we get stuck at x longer than we would like to. And so what is that saying back in this world? That's saying that the implied w is very large. Okay, and so implicitly, what one expects to see is that if these w's have heavy tails, then we're more likely to get stuck at a given state. But if they're well bounded from above, say uniformly in x, then things will not be so bad. You imagine, you have some sort of geometric number of steps to get the behavior that you would perfectly. Okay, so let's talk about these a bit, and I think this is when I have to go to the board, right? So let me keep that up. I think the eraser is over here. Okay, so in what I write, I'll just take f and g to be equal to one another, because we know that for the long-time behavior, that's the object that matters. Okay, so let me write these out. And remember to think of that as sort of being a probability measure in its own right. And then I will write the acceptance probability here slightly more explicitly, because it will be useful for us in making our comparison. Okay, so I'm no longer writing it in terms of this pi hat. I'm just writing it deterministically as a function of x and the multiplicative noise. This is large enough to read, or? Okay, thank you. Times this delta f. Okay, and then for the second example, now something quite similar. that's somehow single objects. Sorry for drawing these as close together as I have. Okay, so maybe I will take this out and give myself a little bit more room. Okay. So goal one, thank you. Show that L2 of whatever is relevant. Okay, so this is this would be to say the pseudo-marginal approach is not as good as the ideal Acropolis approach. That would be goal one. And then goal two, which is, well, I'll make a bit of a guess first, but goal two would be if W and U are less than some M, almost surely, then we are almost as good. So some constant depending on M times okay, and so what's the story here? So bounded weights give you something that is almost as good. Okay, so as the aims are sort of reasonably clear, this is sort of, you know, the nice way to start with these cases, as you've sort of seen from the examples, is you start off by seeing what's happening when all the perturbations are bounded, make sure you can get a nice proof there, and then there's sort of other tricks for handling the unbounded case, which is what we ended up working on. Okay, so hopefully my lack of preparation doesn't show me up too much, but I think goal one should be doable. My memory is it involves Jensen's inequality. Yeah, okay, that's good. So I think this was first proven by Christoph with Matty in an AAP paper. So for goal one, what we want to say, essentially, is that by having this extra noise in this decision here, that it will push the average acceptance rate down. Okay. Now note that the function min of 1 and r, aka this guy, is concave. So that gives us a sort of a reasonable guess of what to go for. So I just need to know what I'm conditioning on, essentially. So let's see. So what do I condition on for this step? Aha, just functions of x. Yeah, okay, you're right. L2 of pi. So slight abuse of notation, I guess, but okay. So right. So let's focus on fix x and y and look at the rest of it in a way. Okay, and that just depends on x and y, so we can ignore that. Okay, so that's over, you know, So we're just looking at the weights W and U. Then, is it the min one product trick on this guy? Just directly? Yeah. But I have to bring him inside or no? Okay, yeah, okay. Yeah, okay. Okay, and we want to show that this is upper bounded by, so remind ourselves, by W times U. No, that doesn't matter. Just by okay, and then I think we're essentially done because this guy is a concave function of U and W, each of which have mean 1 by construction, right? And so yeah, so because that's concave, so that's the step we're using here. So we're taking an expectation with respect to these two guys. The W and the U are here. It's concave, so we can have Jensen's inequality going the way that we'd like it to. And then we are done. Okay, and so there we're done. We proved the sort of one-sided bound that if you don't have to approximate, then you shouldn't. Okay, sort of a nice simple check to have. So this is specifically for functions of x, which is a point I should have highlighted more, but already it's sort of pointing us in the right direction. Okay, I have a couple of minutes, so I can try to prove the other direction as well. I think that one does use the min product trick. Is that right? Yeah, okay. So for goal 2. So note first, thank you. For any A and B greater than 0, it holds that the minimum okay, let me check that that's the right way around. Yeah, okay. And so we're going to extract a term in that direction. So, right. So what I look at yeah, okay, I went to lowercase q at some stage, and hopefully that's not been a source of confusion. Right, so I have a min of a product. The natural product would be the sort of standard acceptance ratio times the perturbation, so I can expand in that way. Okay, and I should point, this is a very elementary inequality. For studying metropolis type algorithms, it's completely indispensable, basically. Whenever you're perturbing the acceptance probability, this is where the magic is happening somehow. So we've sort of gotten quite comfortable with that one by now. Okay, so let me go back to the Dirichlet form. Dirichlet. Right, so. Is at least okay, times what I will just abbreviate to alpha and x and y for this guy here, the standard acceptance, times the minimum right. And so what do we want to compare it to? So we have, if we look at the bottom, that's the same, that's the same, that's the same, that's slightly different. And so, yeah, and then there's the delta force. And so we want to lower bound that. And so what are we going to say? Yes, exactly. So that's equal to U times min U inverse W inverse, which is at least U times this 1 over m that I started with in my assumption, right? And then putting that all together, I basically have a 1 over m times the Dirichlet form of the ideal algorithm. Okay, and so what does that mean? That means if I have weights that are bounded by m, then the pseudo-marginal algorithm is no worse than m times as low as the original guy, up to some sort of technical details. And so it sort of says what you'd expect, that if you're going to use an unbiased estimator of the likelihood, you should make sure it's very well stabilized. Okay, so okay, I'm running out of time, but I think that I'm happy to get that done. Many thanks to my co-authors for helping me through the proof. It's been an interesting 2 hours. Let me just plug this in for sort of the finale, so I don't keep you all for too long. I'll put this away. But just a bit of recap, essentially. And yeah, thank you. Okay, great. And thanks for sticking through it. I appreciate it a lot. Okay, yeah, I haven't talked about the Gibbs sampling side of things. But okay, so taking stock, so in this Markov chain setting, when is the functional approach applicable and easy to use? What we've found is, particularly in this case of exact approximations, where you retain pi invariant reversible structure, and you sort of take some step that you would like to do exactly, and you replace it with a principled Monte Carlo approximation, is very well suited to this case. The kind of perturbations you're doing in this world are very well suited here. As I sort of tried to say before, the fine details of the approximation rarely matter very much. You know, as long as you can control some bounds or some moments, you're in good shape. Yeah, and so if, yeah, as I said, if you have some bounds, then you'll be able to prove something, and we've sort of pushed that forward a lot in the last couple of years. So just to give a bit of an overview of the goals. So what is nice about functional inequalities is, in a way, they let us talk about the convergence behavior of a process at a very large scale, at sort of coarse graining out a lot of stuff that we know might not matter. And so we find that this is sort of very appealing in high dimension, often in cases where sort of uniform bounds on the curvature or convexity are not available, but you sort of know that the large scale structure of the problem is helping you out. But probabilistic techniques are sort of a very nice way of starting thinking about these things. You sort of, you know, as a general rule of thumb, solve the strongly log concave case first, and then think about doing something a bit more general from there. That's usually quite insightful. So some good and some bad about this approach. So from my point of view, a functional inequality, it's a very nice way of sort of sensibly saying this measure or process is nice, right? In a way that doesn't depend on very strong shape assumptions, let's say. And the sort of global nature of the inequalities is instructive. They compose very nicely. You know, we've seen a few examples of that, and that's sort of what I like most. And it's particularly useful for the analysis of what I would call meta-algorithms, right? Where you take some MCMC or whatever and plug it inside some other part of an algorithm. Okay, So Andy talked last week about hybrid slice sampling, for example, which is a very nice example of that we've worked on. The hard work, okay, so proving a functional inequality from scratch can be difficult. We have these transfer principles, but sometimes they're not enough and you have to work a bit harder. There's sort of different types of process where it's not so easy to adapt necessarily. So if you're working with a process that's inhomogeneous in time, maybe adaptive, maybe non-reversible, maybe you don't know the invariant measure, again, you have to work hard again. It can be done, but those are challenging cases anyways, I would say. Building intuition for functional inequalities can take a little bit of time, but hopefully it's sort of, today could be a step in the right direction. And of course, there's always some conservation of mathematical difficulty. If you have a very hard problem, throwing the functional approach at it doesn't necessarily fix it, but there are cases where it works very well. Yeah, so the short recap is sort of the toolbox of Markov processes and how to study their long-time behavior is very vast. There's lots of ways of doing it. Some of them are compatible with one another. My experience is that going the functional analytic route is quite accommodating. Often if it's nice in some other way, it will stay nice functionally. And lots has been done already to make life easier. So it's sort of quite a nice industry. So when studying your next Markov process, whether it's a concrete thing or an abstract thing, maybe a meta algorithm, as I said, I think the functional approach is a nice tool to draw to, and it might be able to offer you something. So I think I will finish there. Thank you.
That's very important. More or less out of time, but we can have a question or two, and then will be Kate next door. So that's 2 minutes. Yes.
So maybe I missed it for your second goal on the board. For what kind of your functions also have to be on?
No, for this one it's general, fortunately. Yeah, so as long as the integral exists and so on, you're okay.
Like fact that for the goal one you have to restrict to functions on only the first coordinate. Does it make you use some information on the conclusion, or?
So I want to be careful about it, but it certainly means, if you can't make the inequality better than this for those functions, then in general it can't also be better than this, right? So that's one way of describing the conclusion. Yes. Yeah.
For functions that are okay.
Yeah, because in the convex ordering, a constant estimator is a very good estimator. Cool. Yeah, I think just to say, if people want references on this sort of stuff, I've included them already, but actually there's some bonus slides here that reference sort of books and lecture notes that are quite useful for many of these topics, which I think, were very useful for me in my education on this sort of thing. Yeah, and I can wrap there and we can go for cake, perhaps. Thanks.